Okay, so stay with me on this because this is some real critical information. The modulation transfer function versus the pixel size. Let's think about a sensor that has lots of discrete pixels. They're all the same size. Each pixel, you can think of each pixel pair as a line pair. Line pairs, as we saw before, were measured in line pair per millimeter. And now if we take a look at the Nyquist theorem, which either you know or you don't, but take my word for it, it says that to accurately reproduce a sampled signal, you must sample at least twice the highest frequency of the signal. So if we put that in a formula to resolve a pixel of X microns, we need to have at least 1/2 times 1 over the pixel size. And since we measure this in millimeters, we're going to have to convert from microns to millimeters. This table on the right shows what the MTF would be for standard pixel sizes. So in the Sony 1/2 inch ICX 414 VGA sensor, the pixel size is 9.9 microns. And that would say, by the formula, that we have an MTF limit of 50 line pairs per millimeter. At the bottom of the table is 2.2 micron pixels that we find in the 5 megapixel Aptina CMOS sensor. And that requires 227 line pair per millimeter. So we can plot this information and see how a lens will perform against a certain size pixel pitch. Okay, remember these numbers for later on. A little quick background here. Usually, the more pixels you have, the smaller the pixels get. This isn't always true, but usually this is what happens. For instance, if we have a 1/2 inch sensor that has a width of 6.4 millimeters, if it has 640 pixels across, each pixel is roughly 10 microns. If we double the number of pixels and make it 1280, each pixel is 5 microns. Unless you make the sensor bigger, which in this case we didn't do, more pixels equal smaller pixels. Now what you could do is you could trade off spatial resolution versus optical resolution. You could see finer details as you put more pixels in the same field of view, but if the pixels are smaller, you must have the optical ability from the lens to resolve them. So here's a picture of this graphically. We could see the same size sensor, and we're going to say that this has 640 pixels across on the left, and on the right it's going to have 1600 pixels across. We can't show this many pixels, of course, but you can see that the boxes that are bigger here will have more of the filament and therefore less resolution than if we go over to the right side, and we could see that the smaller boxes or pixels have less of the element in there, so you have less windings, you get more resolution as you could see more detail, on each picture here. Now let's take a look at the same lens, but I'm going to change the sensor around. In this case, on the left, we have a low resolution camera, while on the right, we have a high resolution camera. Clearly, you could see the numbers much better, and you could see a little bit more of the colors. They don't blur together as much. Now, this is our aha moment. Here we have the same sensor, but we have different lenses. Here you can see where a better lens will show more resolution, especially when you're trying to do some measurement. Right? Here's what we're going to look at. On the left, you can see that if you were trying to count the number of dots, a lot of them blur into each other and you wouldn't get an accurate representation. On the right, the dots are discernible from each other And if you wanted to calculate them, the size of them, the number of them, you can calculate that much more accurately. So here we have the same resolution camera, but this is what a better lens will do for you. So how do we measure how well a lens performs? One way of doing that is the star target. So this is a circular pattern of black and white wedges. Radial pattern allows you to test for astigmatic errors. And the wedges have continuous frequencies that can be calculated by the radial distance coming out from the center of the wedge. You can see that the line is getting thicker going out, and it's going to be easier to resolve on the outside than on the inside. So a standard lens comparison test here that you're looking at will show a bunch of star patterns. Here we have two diagonals so we can see what's happening radially and astigmatically, as well as an up-down pattern. And what we're going to do is we're going to look at different parts of the pattern and compare two lenses, one on the left, one on the right. So here's what we're seeing from the middle. Here's what we see down. And here's what we see on the edge. And you can clearly see that the lens on the right is not performing as well as the lens on the left. Now, let's take a look at another lens here. This is a 6mm lens. 6mm is a very wide focal length lens. What we're going to see again on the left and the right is clearly the lens on the left is performing much better, and you can also see it performing better astigmatically on the bottom left.